Okay, so we've wound up at this question. So what very concrete answer on it? Dimension one being the case when is a space quasi-symmetric to a tree. This is which says that X is a quasi-tree if and only if there is some delta such that for every X and Y in X, and well, then so for every X and Y in X, every path from, so every single path from X to Y comes also close to the midpoint of X and Y. Okay. Well, pick one point whose equal distance to both of them and on a geodesic. And yeah, and then afterwards, it didn't matter which one you picked. Yeah. So there are different ways you could generalize this. One is there's a recent preprint of Asymptotic Fujiwara where they characterize which spaces are quasi-symmetric to cacti, which is some generalization of trees, which maybe has two cut points or something, but that's not the direction that I'm going in the direction of to the tree. So as this, but there are some examples, or there are quite lots of positive examples. So here's a nice of Haglund Wise, which relies on work of Bonk and Schramm. This says that the symbolic group is quasi-symmetric to a Katsuri cube. And there are also so let me just say something imprecise. There are many kind of higher rank hyperbolic examples. Including mapping groups are quite special cube complexes. So all the things that are quasi-symmetric cube complexes, and this is also showing that well, that just being quasi-symmetric cube complex is a lot more general than being cocompactly cubulated because they're Petyt and therefore don't have any unbounded action on a cube complex. Even though they don't have any unbounded action, they can still be quasi-symmetric. So yeah, the fact that you can't really expect any equivariance. Yeah. Yeah. So we don't know whether plus we don't know that there can't be any. Yeah, it's quasi probably not covariant. Well, it's not because they don't have they don't have any proper actions on K0 spaces. So yeah. Okay. But before, okay, I just wanted to outline of the of Hagelin and Wise about hyperbolic groups. Just it's not really going to be relevant for the rest of the talk, but I just think it's a nice thing, and it's a cool outline of a proof. So I thought it would be. So I just thought I'd say it. Just I like it basically. So sketch. Of Hagelin Wise function. Okay, so the first thing is to show. So okay, the first step is. Okay. First step, you show that you use the fact that you're a group. You look at the hyperbolic. You look at the Gromov boundary, and you can show that this thing has finite Nagata dimension. Okay, so that's whatever that is. But what that means is that then you can apply Asymptotic's theorem. The top line is just a black box that lets you apply Asymptotic's theorem, which says that the boundary of G can be embedded in Rn for some n by Lipschitz embedding. Then what you do is you view Rn as the boundary of hyperbolic n+1 space minus point. Yeah. And this gives you a quasi embedding of your group in hyperbolic n+1 space. Now, okay, so this part is von Schramm, and then the Hagelin-Wise part is there are cocompact lattices in hyperbolic space that are cubulated. And it's a fact that any quasi embedding of a hyperbolic space in a hyperbolic cube complex well, given any such thing, you can to get a smaller target that you're quasi-isometric. Okay, so that's the kind of that's the outline of that proof. Finite dimensionality metrically embed the hyperbolic. Use this fact. Restrict. Anyway, like I said, that's an aside. I just like that proof outline. What I want to focus on, yeah. If you're it's possible, and that's actually the question that yeah, I mean, when I get there, it will be an obstruction to being a coarse medium space that we get, which is an obstruction to being QIC. But yeah, yeah, coarse medium groups that are not QIC complexes as well. I don't think I have examples. Yeah. Like, oh, it's pretty easy. It's yeah. You show, depending on what you allow yourself to assume, it's pretty easy. You can it's pretty easy. This map is automatically quasi-medium. Yeah. What I'm going to focus on is the negative direction of the question and finding obstructions to being quasi-symmetric to a Q complex. So this is the theorem. This is kind of a slightly sketchy version of it. I'll say something more precise later. This is just to kind of give a direction so you know where we're going. For each n at least 2, there is an explicit family of cat0 spaces xn such that if is a space that admits a quasi-symmetric embedding from one of these xn, then y is not quasi-symmetric to an n-dimensional Q complex. Okay, so that's the direction of heading. So aside from needing to be, well, a quasi-geodesic space, there are some easy obstructions to being QI. Hold, then you or things like then well. So, but aside from this is kind of maybe the first more. Well, I don't know. This is just another obstructions. Aside from those, it can handle other things than those. Yeah. Okay. So as motivation for the construct, so what I'm going to do next is show how to construct these spaces. As motivation for the construction, remember that the first non-cat zero cube complex that you look at is just three squares glued at points. Okay, because this fails the link condition here. And so if you're trying to find something that prevents you from being QIC Q complex, one thing that you might think of doing would be to, instead of just having three squares, take three quarter planes. This. Oh. God, that's so bad. But the problem with this is this thing, it's got this cone point here, which is bad news for actually being a cube complex, but you can smooth this out. This is actually quasi-isometric to the Euclidean plane. This one cone point here can be smoothed out. So the idea would be to have a lot more of these bad points that are breaking being a cube complex and kind of have them all over the place. So, okay. Definition: a richly branching flat of rank n consists of Rn with, okay, so let's draw the n equals 2 case at the bottom. So you start with R2, and then you have n plus 1 families of parallel codimension. So in the n equals 2 case, you've just got family. And a half glued along each. Okay, so here we've got a half flat glued along this one here, half flat glued along this, and then where's the other one there? Okay, and these ones that are branching off, they're only in section with space. You just got the flat, and you've got things kind of sticking off in multiple different directions. Yeah. Okay, so n plus 1 or more. You only need n plus 1 of them. And okay, these are the spaces that appear in the theorem. And so the natural setting for talking about cube complexes, which is a fine thing, hinting at is coarse medium spaces. I want to talk a little bit about what coarse medium space is. It's quite technical, so I'm not going to be. One motivation for it comes from hyperbolic spaces. So let's just state a fact about hyperbolic spaces. we haven't seen before, but so let X be delta hyperbolic. For any finite subset, is a tree and a quasi-isometric embedding of the tree, where the constant depends on the cardinality of the sets. That sends the leaves of the tree bijectively to the tree. So here are 5 points, and then the tree is embedding something like this. And it says property. And the idea of coarse medium space is to replicate that replacing trees by so higher dimensional trees. In order to make sense of how you actually do this, I'm just to add this fact. How do I want to say this? Every 3 points have a coarse center. Just write that down. Okay, and collectors, and in particular trees also. And the extra fact that I want this map respect these median structures. Again, and the map. So a coarse median space is a space X with a median map that satisfies some conditions, but one of which I'll say there's a sequence HN such that if you take any finite set, then there is a cat-0 cube complex that approximates that subset in the sense that it respects, the approximation respects median structures, and the quality of the approximation is given by this sequence in particular. It just depends on the cardinality. Okay. There exists Hn such that if A is finite, then there's a cat-0 cube complex. And a map medians. Up to the dimensions of the, so if you can always take Q to have dimension at most n, we say that X has rank at most n. So examples, so hyperbolic spaces over there. It's this, the Q in here is just the tree that was over there, so hyperbolic spaces. There are cube complex as well, because you don't have to really do any approximation. You just take the convex hull of your finite set. And it's the quasiisometries. Yeah. Also, in fact, being coarse median of rank 1 is equivalent to being a hyperbolic space. So not that gave us one direction, the reverse direction is also true. And if you're a cat-0 cube complex, then rank is bounded above by the dimension of the cube. So you might actually, it could be lower. You just took a tree and then glued on a couple of squares. Kind of large dimension of it, and you change things in the small scale. It's another version of the no, stop. So, is that I want to phrase this. There is no quasi-symmetric embedding from a richly balanced class. Of rank n to a coarse median space of rank at most n. And in particular, because being quasi-symmetric to a cube complex means your coarse median of rank at most n. Good. Okay, so last few minutes about the application to, I'll get down here, to tubular groups. Okay, so definition. A tubular group is a group that splits as a graph of groups with z squared edges. Okay, so there's one, in fact. So it's by taking and then moving along disk. Yeah. So we're drawing this one. Okay. And okay, and the slopes are the images of the adjacent. Up to commensurability. So it's really just direct. You can including the yeah, so this okay, and so the property of this theorem is that if any at least 3 slopes then G is not quasi-isometric to a cube complex. Okay, and then so he for having a free action on a cube complex, a free action, and he also shows that some tubular groups related, but he has some. I don't remember exactly what the condition is, but this equitable set definition that shows that you have a free action on the cube. So so I think the example here wouldn't be the equitable. So there are tubular groups that are freely cubular, but not quasi-cubular. Yeah. This one? You look in the asymptotic cone, and then you have this base flat here. And then you've got these. Use Bowdich's quasi-flats theorem, which tells you that this base union of orphans, it's a median approximation. It's actually a median map. And then these show that these things can't happen consistently with each other. Well, yeah, I mean the thing you need is that they're not they are incompatible directions somehow in the cone, but it's not clear how you would do that. Like you can be able to do that in general, include them. Yeah. There could be versions where they're allowed to intersect each other. Maybe if these two flats along this actually being disjoint from each other, then you need three.